Welcome to the ALU stage of CHUMP, a homemade computer. The ALU, or Arithmetic and Logic Unit, is essentially the number crunching part of the processor. This is it, and it has 16 distinct logic and 16 distinct arithmetic functions. Using this ALU Explorer circuit, I will demonstrate 2 arithmetic and 2 logic functions. But before I do, I'm going to describe the layout of the Explorer. So essentially the green LEDs here display the function sections, which selects which function of the ALU is used. These 2 yellow nibbles echo the inputs, and finally the red nibble is the outputs. So the first function that I'm going to demonstrate is the logical function f equals not a. So as we can see here, the logical function f equals not a is when all the select pins are low. So going back to our Explorer, setting all of them low. So we also have to make sure that the M pin, which selects between arithmetic and logic, is high. And then essentially it'll just invert whatever's on the A input. So we have high, low. Then on the outputs we have low, high, low, high. And if I switch around these, so it still echoes it, all lows becomes all highs. And then of course it'll just ignore whatever's on the B input no matter what I do with the A. The next function I want to present is the logic function f equals a or b. So going back to the data sheet, we can see that the S inputs are high, 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 and low. So the plus symbol here actually just means or, it does not mean plus. If it was plus the arithmetic operation, it would be plus in all caps like it is here. So on the Explorer, if we go high, 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 low, then it'll essentially just do a bitwise OR. So it'll take any high signal from either input and it'll pass it through on the outputs. And then of course, if 2 of the same bit are selected, it will only take 1 and it'll be the same as you'd expect with OR. Next, I'm going to switch to arithmetic mode by flipping this switch to low. So the first arithmetic function that I'm going to demonstrate is a plus b. So going back to the data sheet once again, we can see that a plus b is here, and it's high, low, low, high. So on the Explorer, high, low, low, high. And once again, it behaves exactly as we expect. Here we have the number 5 and the number 4. So when we add them together, we know we should get 9. And we can see 8 plus 1 is indeed 9. The thing that I find interesting about the addition circuit is that if I set them all low, it almost behaves similar to an OR gate. So at least it does when no 2 of the same bits are selected. So if we have this configuration, for example, if you just look at this, you can say, oh yeah, that's OR, because it looks like it's just ORing the 2 bits. But then as soon as you flip 2 of the same bit, like for example, these 2, then it becomes different, but it's just a cool feature of the adder. Anyways, the last function I'll demonstrate is f equals a minus 1. That is the very last function on the data sheet, and as we can see, it's when all the S pins are high. So going back to our Explorer one last time and setting all of our S pins high, just like the first f equals not a, it will ignore anything on the B output because it's just looking at a, and it's just subtracting 1. So if we have 1, we get 0, just as you expect. 2, you get 1. 3, you get 2, and so on, all the way up to 15, you get 14. So now let's get into how the ALU is integrated with the rest of CHUMP. To control the ALU, 5 bits control the S pins and the N pin. These are decoded from the opcode in the program ROM. An additional control bit selects between a constant and a number stored in RAM on the B input of the ALU using a multiplexer. The A input of the ALU is tied to the accumulator, and the output is stored to the accumulator. This means that the f equals b instruction is used to store a value to the accumulator, while new data is inputted using the B input. For example, to add A and B together and store its result to RAM, it would take 3 Chumpinese instructions. First, A is loaded into the accumulator using the load instruction. Then B is added to A using the add instruction. Finally, the store to instruction is used to store the result to a location in RAM. The ALU section of CHUMP is what gives it its computational power. In the final stage of CHUMP, its inputs and outputs can be rewired and optimized to act as a microcontroller, somewhat like an Arduino, and the ALU will be what is able to switch its inputs to the desired outputs. Thank you so much for watching, and I'll see you in the next stage.